In this video, we're going to talk about the derivatives of some trigonometric functions. Now that we know our power rule, our product rule, our quotient rule, we're going to put those together knowing our trig functions. So remember, if we're finding a derivative of a function, we're trying to find the slope all along that function. So if I'm given the graph of y equals sine x like I have here, I can sketch a graph of its derivative based on the slope. Well, I know at this maximum point it has a slope of 0. At this minimum point, it has a slope of 0. And then I have to look at what's happening between those 0 slopes. So as I'm coming along from this 0, I'm going in a negative direction and it's getting very, very negative till here. And then it starts getting less negative and it goes back up and approaches 0. So if I want to sketch that, I see that it's coming down, it gets steep, and then it goes back to 0. Similarly, over here, it's 0, and it's getting steeper and steeper and steeper, but it's in the positive direction. And it's getting as steep as it goes. And then I can do the same thing likewise on this farthest left section. It's a positive slope. Starting at 0, 0, it's positive. It's really positive, and then it's getting less positive. And so we'd say it's coming up over here. Now, if I take a closer look at this graph, we can see this should look like a very familiar graph because this is the graph of cosine. So that tells me that if f of x equals sine of x, by graphing its derivative, I'm able to see that f prime of x is just cosine of x. So these are one of our special functions. When we're dealing with trig functions, we need to know how to take those derivatives. Alright, so we figured out what the derivative of sine is. Let's do a similar technique to find the derivative of cosine of x. So again, here's my graph of y equals cosine x. Derivative is finding what the slope is at all the points. So I know right here, at 1, the slope is 0. At pi, my slope is 0. And at 2 pi, my slope is 0. And so then I take a look again, and I see what's happening between those zeros. So right here, when x is 0, the slope is 0. And then it starts decreasing. So I now have a negative slope and it gets really steep. It's the steepest right here. And then it's getting less steep as it goes back up towards 0. So if I sketch that, we said we're starting at 0. It gets negative. It stays negative. This is all below the x-axis, so it's all negative and then gets steep again. And then I look again. Now I still have a 0 slope, but it's positive. It's getting really steep. And then it's getting less steep, but it's staying positive, which means it's always above the x-axis right there. So again, looking at my graph, cleaning that up just a little bit, I can see the graph kind of looks like this. Now remember, this is just a rough sketch. This is not precise. And we should see this looks really similar to a sine graph, but it's not quite a sine graph. So remember, our original function f of x was cosine x. And we're trying to figure out what is the equation of f prime of x that we drew. Notice it's an upside down sine curve, so this is equal to negative sine of x. Okay, so we can go through that same type of thing to get the derivative for all of our trig functions, but here's a table for you. You do need to know these. Derivative of sine is equal to cosine. Derivative of cosine is equal to negative sine of x. Derivative of tangent x is secant squared x, and you could get that using a quotient rule. If you rewrite tangent as sine over cosine and then go through the quotient rule for the derivative, you would end up with secant squared. Derivative of cotangent of x is negative cosecant squared. Derivative of secant of x is secant x times tangent x. And the derivative of cosecant x is negative cosecant x times cotangent x. So for extra practice, you can get all of these. But in order to be able to do any of these, the two basic ones you need to know are these top two, derivative of sine, derivative of cosine, and all the rest we can get by writing the original problem in terms of sine and cosine and then using our derivative rules. Okay, so just some practice. So I'm given f of x equals x squared times sine of x, and I want to find f prime of x. So notice this is a product. I'm doing x squared times sine x, so I'm just using my product rule. So f of x equals the first times the derivative of the second plus the second times the derivative of the first. Now I'm just going to rewrite that just a little bit because I always like pieces in front. So I have x squared times cosine x plus 2x sine x. And the reason I like to put those out in front is I don't want to accidentally think that I can multiply this x and this 2x and change the angle. The angle does not change. Sine of x is a function, and that stays its own little piece. All right, so another example. F of x equals cosine x sine x. We want to find f prime of x, find our derivative. So again, this is a product, cosine x times sine x, so I'm going to use my product rule. So f prime of x is equal to the first, which is cosine x, times the derivative of the second, derivative of sine x is cosine x, plus the second, sine x, times derivative of the first. Derivative of cosine x is negative sine x. So I clean this up a little bit. Cosine x times cosine x we write as cosine squared x. We put the squared on the function cosine, so we know it's the whole thing that's getting squared, minus sine squared x. And if you remember your trig identities, which this is, we're going to start using those. Remember, we did review trig at the beginning of the course. Cosine squared x minus sine squared x is actually equal to the cosine of 2x. This is one of our double angle formulas. So f prime of x is equal to the cosine of 2x. All right, this example makes us use the quotient rule because we have sine of x divided by 1 plus cosine x. So I'm going to say my u is that top function, sine of x, and my derivative of u prime is just cosine x. I like to write out my quotient ones. V, the lower function, is 1 plus cosine x. V prime, derivative of 1 is 0, derivative of cosine x is negative sine x. So to get my derivative, f prime of x, that's low, 1 plus cosine x, d high, so the derivative of the high was cosine x, minus high, sine of x, d low, which is negative sine x, all over the low, 1 plus cosine x, squared, right? Low d high d low, low squared. It's my yodeling time. All right, so now I have cosine x plus cosine squared x plus sine squared x all over 1 plus cosine x squared. And then I say, oh, wait a minute. Cosine squared x and sine squared x, that's another one of those identities we're supposed to know. That's the Pythagorean identity. And that's just equal to 1. So I have cosine x plus 1 over 1 plus cosine x squared. And so this simplifies because cosine x plus 1 over 1 plus cosine x is just equal to 1. So I have 1 over 1 plus cosine x. So here is my derivative. Okay, again, now we're going to start with f of x equals sine of x. And now I want to find f double prime. So that just means find the second derivative. So I'm going to do it the whole process twice. So we know the derivative of sine of x, so f prime of x, is just equal to cosine x. And now I take the derivative of this piece. So now I'm doing f double prime of x. So the derivative of cosine is negative sine of x. Okay, so here for a reference is all of those trigonometric identities. You have all of your reciprocal identities. Up here that we need to know are Pythagorean identities. Again, the one I think that is the most important to know is to make sure we know sine squared x plus cosine squared x equals 1, and the others fall out of that. We have our sum and difference identities. We have our double angle identities. We have our half angle identities. So we used this cosine 2x equals cosine squared x minus sine squared x earlier. These, you can find these in your book. You can find them in tables. If you do a Google search for trig identities, you can get pages of tables of these. Make sure you have these handy if you don't know them off the top of your head. We do need to use these, especially as we start getting into more complicated derivatives that we might need to simplify.